The big success of model checking is due to the fact that there are automatic algorithms for finding out whether or not a CTL formula holds of a transition system. In this section we're going to illustrate the general approach. For state-of-the-art solution, of course, one has to go deeper in the choice of data structures and algorithmic details, but this will suffice to give you an insight that in fact model checking is something that can be done fully automatic. The algorithm focuses on state formulae only. That means we always consider the A or the E operator together with one of the X, F, and G, as when we were first introducing the intuition behind formulae in CTL. So, for state formula, we're going to compute the set of phi, which will be the states in the transition system where the formula holds. For some formulae, this is pretty easy. For an atomic proposition, the set of states that satisfied are simply the ones where the atomic proposition is one of the labels of the state. For conjunction, we just take the intersection of the states that satisfy respectively phi 1 and phi 2. And for negation, we take the complement with respect to the entire set of states. Also, the formulae reachable in one steps are fairly easy to deal with given our simplifying assumptions. Recall that reach 1 expresses a set of states that are reachable in one step, starting from a state in the argument to reach 1. So, the formula for Ex of phi gives us all of the states var sigma such that what is reachable from var sigma in one step will contain a state that is also satisfying phi, or written as here, the intersection between the set of states reachable in one step from var sigma and the set of states satisfying phi is non-empty. For Ax of phi, we take all the states var sigma such that everything reachable in one step from there will be contained in the set of states satisfying phi. Let us take inspiration from these two equations and change our consideration from reach 1 to reach, the set of states that is reachable in 0, 1, 2, or many steps from the argument set of states. For the first formula, we're then looking at the set of states var sigma such that what is reachable from var sigma in any number of steps intersects in a non-empty way with the set of states satisfying phi. That is the formula for getting the set of states that satisfy EF of phi. For the second formula, where we're asking for those states var sigma such that everything reachable from var sigma must be contained in the set of states that satisfy phi, we in fact get the formula for AG of phi. Looking at one of the more complex cases, we shall look at EG of phi. This is a formula that says that from the current state there is a path upon which phi holds all the time. The approach we take is illustrated on the right. We start by looking at a set that is too large, namely all the states that satisfy phi, and gradually shrink it by throwing out offending elements until it can't be shrunk anymore. What is left will turn out to be the set of states that satisfy EG of phi. The algorithm on the left illustrates the approach. A set of states S, not to be confused with a set of states of the entire transition system, is initialized to the set of states satisfying phi. Then we continue to look for offenders and throw out the offenders. Being an offender means that we have a state var sigma in S, none of its successors in one step is in S, then we throw it out. This also gives us a way to deal with another formula, A of phi, because thanks to our simplifying assumptions, we have a nice law of double negation. So AF of phi is in fact equivalent to the negation of EG of the negation of phi. And since we already have the algorithms for dealing with EG and for negation, we can put these things together and get an algorithm for AF of phi. The cases of until both for exist a path where phi 1 holds until phi 2 and for all paths phi 1 until phi 2 can also be handled, but you'll have to read the text for getting those details. So now is the time to read the section in the book and doing the try-it outs on the way.